Now is it fine, sir?
It is audible. It is audible.
Yes, sir. Okay. Since we have actually adjusted the entire schedule for 3 days, we do have continuous sessions. I hope that the participants will bear with us. And today we are going to start our second session. The second and third sessions for the day will be hands-on sessions driven by Dr. Satyam Agarwal from IIT Ropar, India. He is actually presently working as an assistant professor in the Department of Electrical Engineering at IIT Ropar, and he obtained his PhD in Electrical Engineering from IIT Delhi in 2016. And prior to that, he completed his MT degree in Signal Processing and Communication from IIT Kanpur in 2012. Before joining IIT Ropar, he has also served as an assistant and professor in the Department of Electrical and Electronics Engineering at IIT Guwahati. Additionally, in 2017, he worked as a postdoctoral research at Politecnico di Torino in Turin, Italy. Dr. Agarwal's research focuses on wireless communication networks, particularly next-generation networks, beyond 5G, 6G networks, and architecture and airborne UAV networks, unmanned aerial vehicle networks. He has been recognized for his work and received the DST Inspire Faculty Award. Has also secured several research grants from organizations such as DST CERT, ISRO, the Ministry of Earth Sciences, and the Punjab Skill Development Mission. Dr. Agarwal also contributed extensively to his field, having published over 30 research articles. He is an esteemed senior member of professional societies like IEEE and all. Thank you, sir. We are very fortunate to have you as a speaker for our 3-day technical workshop. And I hope that your sessions will be fruitful to all the participants. Thank you all. The session is yours, sir.
Thank you so much, Dr. Sharath, for the nice introduction. And I would also like to extend my greetings to Dr. Sushant for inviting me for this workshop.
Thank you, sir.
Let me share my presentation.
Yes, sir.
I hope my presentation is visible to everyone.
Yes, sir. Yes, sir.
All right. Okay. So, this session and the next one is what I'm going to do. So this first part will be on simulating a basic wireless communication link. What we are going to do is that we are going to do a hands-on session on MATLAB. So first we will understand the theory part, and then we'll program this communication system, a very basic one, on MATLAB, and see how we proceed simulating such kind of systems. And then in the second part, I'm going to take the multipath fading part of the wireless channel and show you how do we model such kind of wireless channels in MATLAB. So basically what's this talk aims at is to make you understand the basics of wireless communication systems, specifically the wireless channel, the modulation, the demodulation, and also make you understand how to take this theory part to the simulation environment and then do your research, build on your research on those kind of settings. And of course, what I'm going to discuss with you will, if you want to do some practical implementation as well, I will give you sufficient knowledge that you would be able to do even the practical implementations. At our lab at IIT Ropar, we do a lot of practical implementation of these systems. We have got these software-defined radios. Probably you might have heard about it. We have got a lot of them from different vendors. They come in different shapes, sizes, and different capacities, different specifications. So our lab works extensively on these things. So I'll take you through this very exciting journey of communication systems. I would say it's very exciting because it always fascinates me how we are able to communicate to a person without even seeing him, and that too without being connected on a maybe connected in terms of wire connection or so on. So it gives me great fascination. And this was actually when I was in my school. So I was fascinated about how these TV remotes work. And then I thought, okay, I'll do something in this area. And then I landed up into the wireless communication systems. And very exciting field. It is a very exciting and buzzing field, as you all know. Broadband has become a necessity, which is equivalent to electricity and water. So if you don't get broadband now, you would rather feel empty. You would say, oh, something is missing in your life. So this has become almost a necessity, and all these different applications are now built on these wireless systems. Particularly, we are seeing the 5G advent. We have been extensively using Wi-Fi for quite some time now. And you see Wi-Fi being deployed in each and every area. And of course, Bluetooth is one more technology that we are using pretty often. So that's why, and of course, this after 5G, we are looking at 6G. Then of course, newer generation of communication technologies are going to evolve. So we see a lot of research, innovation that is going to come up, is coming up and going to come up in this field. And it would be worthwhile to understand it in a very structured and detailed way so that we can also contribute in this particular area. So with that, let's take this exciting journey. So I'll start first with the digital modulation scheme. Now the whole session of mine will be it will be basic, but even if you have taught this course or you have taken this course multiple times, still you'll feel some newness in this, because what I have done is that I've tried to summarize what the different books do, what the different notations teach you about. I've tried to summarize everything into one so that I can give you a complete picture of how a communication system looks like. So all of you might be knowing modulation. Why we do modulation? We do modulation because we cannot transmit low frequency message signals over the air, primarily because you would require large antenna size, or you won't be able to do multiplexing, or you won't be even going to transmit at larger distances, and so on. So that's why you use modulation. And in modulation, what you do is that you take a high frequency carrier signal. Now here, this higher frequency carrier signal I have denoted by FC here. So this is a high frequency carrier signal, and you want to modulate this particular carrier signal with respect to some message signal. So message signal is what you want to transmit. Now, what are the properties of this sinusoid or this carrier signal which you can change? So you know the broad two things that you can change in a carrier or in a sinusoid is its amplitude and its phase. Okay, so one thing is that you can change is the amplitude and phase. Now, based on what you are changing, you give different names to such kind of modulation schemes. You say if you're changing amplitude, you say amplitude modulation. If you are changing phase, you say phase modulation. If you are changing frequency is a part of phase, or you can say it's part of the angle modulation. So so this phase and frequency modulation, they are interrelated to each other, and both you can say it's part of the angle modulation. Now, if you have an analog signal which is changing this amplitude and phase, then you say analog modulation schemes. If your message signal is a digital signal in the form of, say, bits, then you call it as a digital modulation scheme. Okay. Now, what we do is that we try to change using this digital signals, whatever message signals you have in the form of the binary bits. You want to change some of the properties of your carrier signal based on that. Now, here I've shown you the carrier signal, the carrier with this part cos. Okay, this is cos. Okay, I can expand this signal. I can write it as, so you know this cos A plus B is there. So you have A cos 2 pi fct plus phi, where your fc is your carrier frequency, phi is the angle that you're changing or the phase you're changing, and A is the amplitude that you're changing of this carrier signal, of this carrier frequency fc with respect to your message signal. So I can expand this particular expression. So this is cos A plus B. I can write it as cos of A into cos of B. So I can write this A cos 2 pi fct cos phi minus A sine 2 pi fct sine phi. Okay, I've just expanded it. And now what I can do is that I can take these two things together, A cos phi, and I can take these two things together, A sine phi, and I will call this as AI, which I'm defining it as A cos phi, and I can say this AQ, I can define AQ here, which I'm defining it as A sine phi. So I can write this overall S of xt as AI cos 2 pi fct minus AQ sine 2 pi fct. So these two forms are equivalent. You can see that. Now, why I have done this is that I want to show you a very important aspect of this. What we are doing is that you can see this A, I, and AQ is a function of A and theta, A and phi. So because you have two independent variables, that means these AI and AQ are independent in themselves. That means what you're doing is that you're taking your carrier frequency 2 pi fct, and your one carrier frequency is your cos, the other one is your sine, and you're taking two message streams, which is one is AI, the other one is AQ, and you are amplitude modulating them independently on these carriers. One carrier is the cos, the other carrier is the sine, and then you are of course adding or subtracting them together, and then you are forming a composite signal. So what I want to say is that when you are transmitting any signal over the channel, you just don't transmit a single message stream. You rather transmit two message streams at the same time. Or rather, I would say in other words, you have the capability of transmitting two streams at the same time. Why you have this capability? Because you know that the cos and the sine, they are orthogonal to each other. So therefore, this is a very important aspect in our communication systems, that rather than transmitting just one signal here, which is A cos 2 pi fct, we basically transmit two streams, AI and AQ. Now I can even simplify further, and I can write this as AI plus JAQ times e power j 2 pi fct, and I take the real part of this. So this is, I've made a complex notation out of it. So I've written AI plus JAQ, and then here we have the complex exponential, which is e power j 2 pi fct. You know what is this e power j 2 pi fct? It is cos 2 pi fct plus j sine 2 pi fct. So now the important aspect I want to discuss here, very important aspect, whatever signals that we are transmitting or whatever signals we are receiving, these all signals are real, always. Whatever transmission, whatever receptions we are doing, all the signals are real. There is no imaginary signal that is transmitted. This imaginary thing comes into the picture when we want to denote a particular expression in a compact notation. For example, rather than writing these two expressions here, I can very well write it in this complex notation and just take the real part. Of course, you can solve this too. You can multiply ai plus jaq with this cos and j sine, and you can finally take the real part of, you will finally arrive at this expression here. But we deal with the complex notations. Why? Because it makes our life easy when we are doing mathematics. Okay. And you would see in majority of the communication systems books or theory, they use complex notations rather than using complex, the real notations. Okay. Now this AI and JQ, I can write this as A, or let me say AC, which I can say it is a complex envelope. So this is complex envelope. Why it is a complex envelope? Because this is amplitude, you can say, and this is my carrier frequency. So when you're multiplying your carrier signal with any signal which is changing the amplitude of the signal, then you say it's, it is trying to create a envelope of your carrier signal. And because the envelope here is complex, we call this as a complex envelope. Okay. Now these things, these are very small things, but these things should be very clear when we proceed further in digital communication systems. Now, what we do in a digital modulation scheme is, based on the different bits that you want to transmit, you want to change this complex envelope AC. Right? So you want to change AC based on the bit that you want to transmit. Okay. So sometimes what you will do is you'll forget about the complex part, that is, you will forget about the AQ. You will just make changes in the AI, the in phase part. So okay, so I and Q means the in phase and the quadrature. So I means in phase and Q means quadrature. So in certain case you want to just change AI part. In certain other cases you want to change both the parts, the complex and the so that means the real as well as the imaginary part. We'll come to this more detailing little bit later. So this particular slide shows you a comprehensive picture of how from message generation to the signal transmission, what happens to your signal. So what happens is your message is generated somewhere here. And once your message is signaled, so what is your message? You want to, let's say, transmit some file, some data, some voice, some video, or it could be anything else. What you do is you first digitize your message signal. So if you are transmitting a file or a text message, that is digitized in itself. But if you want to transmit, let's say, video or audio, then you do need to have certain converters which can convert your analog signal to a digital signal. So from this starting, you need to have your digital signal here. Now this digital signal can have a lot of redundancies. So you want to remove these redundancies. How do you remove it? By using source coding. I'm not going to go into that source coding aspect, but suffice it to understand that, see, this is a picture, let's say. Now in picture, you have each of these pixels. Each of these pixels will denote, let's say, the brightness of the picture. You can encode each of these brightness in each of these pixels by, let's say, 8 bits. So you will have sufficient amount of bits that you want to transmit for a particular image. And that would be pretty huge. So you want to basically reduce the size of the signal that you want to transmit, then you use some kind of compression schemes, for example, JPG that you commonly use, and so on. PNG you use. So these are certain formats which can compress your image and make it in a small form that you can transmit. So that's the source coding. Now comes the channel coding part. So channel coding is basically, so here in source coding, you remove redundancies. In channel coding, you add redundancy. Why do you add redundancy? Because you want to counteract the effect of the channel. So when your signal propagates through the channel, it is going to change. Some of the bits are going to be flipped because of the errors. And therefore, what will happen is that your signal, whatever is being received at the receiver, it will not be in the proper form. So you want to have a robust reception. So you add certain redundancies to your bit stream so that when you receive it at the receiver, you could understand what are the errors in your signal and maybe correct some of those errors. So popular examples are Hamming codes, Huffman codes, LDPC. LDPC is commonly used in your 5G systems, turbo codes, fountain codes, and so on. So there are a lot of research goes on in the channel coding aspect. Then the output of the channel coding is again the bits. Such kind of a bit stream is there that you want to transmit. Now what you do is, this is the modulation that you do. You take certain number of bits. So you form a set of, you take certain set of bits and form symbols out of it. Okay, so let's say I take 2 bits and form a symbol. So I will say, okay, this is symbol 1. So it's a combination of 2 bits. I can also very well define a combination of 3 bits to be a symbol, or a combination of 4 bits to be a symbol, and that's pretty fine. So it depends on the modulation scheme that you want to use. And now you take this combination of bits and map this to a complex number, which I just discussed in the previous slide, which is AI plus JAQ. You take this set of bits and you map it to a complex number, which is AI plus JAQ. And this is what is your complex envelope that you want to next multiply with the carrier and transmit. So this is your complex envelope, or in other words, you can say it is your digital modulation symbols. So I hope it is clear to you. So it's the set of bits that you map it to one of these points in the complex envelope. So one part is the I, the other is the Q. And you take one of these bits, set of bits, and map it to one of these points in the complex plane. Okay. Now what you do is, now you keep on getting the bit streams, and for each of these bit streams, you are going to get a set of these digital modulation symbols. So for example, for these 2 bits, you get A1. For another 2 bits, you get A2. For another 2 bits, you get A3, and so on. Okay. So this is what you're going to get. And and then what you do is you have to convert. So now this is a digital signal. You have to convert this to an analog signal for transmission. Okay. Now, how do you convert it? You use an analog. You use a digital to analog converter and an analog filter. So how do you do that? You take this set of A1, A2s, and so on, and then what you do is you pass it through a filter. So suppose the very commonly used filter is your rectangular filter, and suppose we are using a BPSK modulation. So what the BPSK does, it takes 1 bit and maps it to only the in-phase part. So it takes either AI to be plus D, and let's say for bit 0, it gives AI to be plus D, and for bit 1, it gives AI to be minus D. And if you're using a rectangular pulse, then what you will do is, so you will get, let's say, plus D here, minus D here, plus D here, and so on. And then you make an analog signal out of it. So what you need to do is you make a rectangular pulse. Okay, so something like this, and so on. Now, To make this analog signal, you need to give something called as a bit duration. This is a very important part. Till now, it was digital signal, but when you are converting it to analog signal, you need to provide timing. How much one particular symbol or one particular bit takes. And based on that, you generate your analog signal. And then what you do is you have now this AI plus JAQ, which is an analog signal. And then it is multiplied by the carrier signal here in the RF filtering and up conversion. So this is what is you have this AI plus JAQ multiplied by e power j 2 pi FCT. And then you have your power amplifier, which amplifies your signal and you transmit. Now what you do at the receiver, you do the similar, the reverse thing. What you do is you receive your signal, pass it through a low noise amplifier, and then you down convert it. Now why you are down converting it? You want to remove the effects of the carrier. So till this point, till point C, if you see, it was all analog signal of lower frequency. When you multiplied it with the carrier, it became a high frequency signal. The reverse thing you have to do at the receiver also. You need to multiply it with the carrier and pass it through a low pass filter so that you get again a analog signal, which is a low pass signal. Okay. So here the C dash, at this point, you get a baseband analog signal. Baseband means signal having a lower frequency. Okay. Now, why you go to the baseband? Because it is not possible to do signal processing in the higher frequency regime. You cannot, so suppose you are using FC to be, let's say, 1 gigahertz. So to process this 1 gigahertz signal, you need, as you must be knowing the Nyquist criteria, you must require 2 gigasamples per second. At least that much samples to process this kind of signal, which is not possible in your digital computers. So what you do is you remove the effect of the carrier frequency, and what you do is you pass your signal through the low pass filter and take it to the baseband. That is, it takes the frequency close to the frequency of your message signal. And then what you do is you now convert this analog signal back to the digital signal. Now, when you're converting the analog back to the digital, again, if you recall, when we were going from digital to analog, we required this bit durations. The same thing is applied here also, bit or symbol duration. You need to give the symbol duration here also, or the symbol clock. So this symbol clock you use to figure out, okay, at what times I would get a different bit or a different symbol. From there, you sample your signal. You know very well the idea of going from analog to digital domain. You sample your signal and then you pass it through your demodulator for further processing. Now, what your demodulator does is that it receives a distorted version of your complex envelopes, AI plus JAQ, and then it tries to figure out, okay, which of the symbols might have been transmitted. And we'll see later how we determine that part. Once that is determined, you convert your symbols to your bit stream. And then, of course, it passes through the channel decoding part. It makes use of this redundancy that you introduced to remove some of these errors that might have occurred over the transmission and reception. And then you do the source decoding and show the message to the user. So this is a very comprehensive diagram of a communication system. With this, I think most of the things are clear to you. Now I want to make little bit of comments on the different kind of modulation schemes. Now, first modulation scheme that I want to touch upon is the quadrature phase shift scheme. So we talked about BPSK, what the BPSK does. So if you have certain bit streams, let's say, so what you do in BPSK, you take one and then you for bit 0, let's say you say A, your complex envelope to be 1 or D, and for bit 1, so for bit 0 and for bit 1, you would say A to be -1, let's say. In QPSK, what you do is you take 2 bits at a time, make it a symbol, and then you have now 4 combinations. So for 0, 0, you will have something, for 0, 1, for 1, 0, for 1, 1, sorry. So in 0, 0, let's say I can say I will have 1 plus J1. For 0, 1, I can say 1 minus J1. For 1, 0, I would say -1 plus J1. And for 1, 1, I have -1 minus J1. So these are all complex numbers, and you can plot them on a complex graph with the x-axis to be I, the in phase, and the y-axis to be Q, quadrature. And you can make these 4 points look in a graph. And of course, you can write this point corresponds to bit 0, 0. And this point corresponds to bit 1, 0. This point corresponds to bit 1, 1. And this is for 0, 1. Okay, so you know that. And such kind of a graph, when you depict your bits into a complex numbers, into complex these numbers, this kind of a graph is called as constellation diagram. Okay, so we'll come across this constellation diagram quite often. So this is about the quadrature phase shift keying. And there are many other modulation schemes also. You might be familiar with these. So here on these I in phase and quadrature axes, I'm showing you the different points which would correspond to different set of bits. So you have QPSK 6 com, 8 com, 16 com, 64 com, 32 com. These are some of the majorly used modulation schemes. Now, so once we have understood the modulation part, we have understood how you carry out the signal processing in communication systems. Then what we do is we start again with the message signal. And how do we generate a message signal in MATLAB? Is we use something called as a randi command. So randi it actually generates random integers in MATLAB. So you can specify what kind of integers you want to generate using this randi command, and how many of such integers you want to generate. So this is what it does, and it will generate to you a series of bits, bit 0, bit 1, and so on. And that could be again used to first modulate, convert this to a complex envelope, and then be transmitted. Now, a very important part is the pulse shaping. So remember, I used the rectangular pulse to describe how do you convert from your digital signal to the analog signal in the transmitter part. And there I said, okay, let me use the rectangular pulse. So when I have complex envelope, say plus D, I would transmit a rectangular pulse of amplitude plus D. And when I have my complex envelope A to be minus D, I would take another rectangular pulse with amplitude minus D. Okay. So this is what I would set. And then what I did is that I wanted to transmit this, that is multiplied with the carrier signal, cos 2 pi fct, and then transmit it. Now, the problem with the rectangular pulses, as you know, is that in the frequency domain, it takes a very wide spectrum. Why? Because in the frequency domain, it is a sync pulse. And you know, the sync ranges from -infinity to infinity. So when we are transmitting rectangular pulses, these are not very efficient in terms of the frequency or the spectrum that it occupies. So instead, what we can use is a rectangular pulse in the frequency domain, which would lead to a sync pulse in the time domain here. And again, this is also not practical because this sync pulse in the time domain starts from -infinity to infinity. And so if you want to transmit such kind of pulses, then you need your receiver to be started at a very long time before, prior to your communication, and it should run for a sufficiently long time after you have completed your message transmission. So this is one of the problems with the using the sync pulses in the time domain. So what people have suggested is use some kind of other waveforms, something like raised cosine or root raised cosine or Gaussian filters, to kind of shape your pulses in the time domain so that you can have a finite time interval over which you can transmit your signal. At the same time, it takes finite bandwidth. So these are some kind of filters, raised cosine filters or Gaussian filters, which are commonly used in our communication systems. So rather than transmitting rectangular pulses, you transmit these kind of pulses. And a simple example I'm giving you here. So here you can see this is an example of a PAM, pulse amplitude modulation. So in PAM, what you do is you modulate the amplitude, or rather what I can say is that you have this A, which is AI plus JAQ. So AQ is always 0. And in PAM, what happens is you change this AI based on the combination of bits that you want to transmit. So for example, I take the set of 2 bits. So if I make 2 bits as a symbol, so I have 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. For 0, 0, I can transmit, let's say, amplitude A to be, let's say, +1 or +0, let's say 0. This could be +1, this could be +2, and this could be +3. So if you draw the constellation diagram, how it is going to look like? One point will be here, second here, third here, fourth here. Of course, it is not efficient one, but it's just for an explanation I have shown you. So this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. Now, if you are using rectangular pulses, as I said, this blue curve shows you the rectangular pulses, and in the frequency domain, you can see it is a sync. And you can understand, you can see that it takes a lot of bandwidth when you're transmitting these rectangular pulses. So what we did is that we applied a raised cosine filter to it. And you can see the red curve is after the application of the raised cosine pulse. So what you did is you replace these rectangular pulses with the raised cosine pulses. And now this red curve here in the power spectral density plot, you can see that your power decreases very drastically as soon as you go out of the band. Okay, so this is the advantage of using pulse shaping filters. Now coming back to the receiver design, how the receivers are designed, I will delve more detail into it. So what you do is that you are receiving some signal. Again, your signal is, your ST is real of A e power j 2 pi fct. Let me write this AC, which is a complex envelope. And what happens to this? It is added with some noise. Now, in general, what kind of a noise we take? We take something called as AWGN noise, additive wide Gaussian noise. I'm going to describe in detail in the next slide. So you get a noisy signal when it gets interfaced at the antenna. And from where this noise comes, actually noise comes because of the random fluctuations in electrons in your complete receiver circuitry. So in your receiver, you have your electronics in which you have electrons because of the thermal because of the heat. These electrons move quite a lot and they induce certain changes in the current, in the voltage, and therefore you get a noise in your signal. So therefore we use this low noise amplifier here. No noise because if you use a normal amplifier, it is going to give you more noise. So therefore we use a low noise amplifier so that the device must not introduce more noise into the signal. And then what you do is you have a down converter here. Now this down converter is very important. Now, whenever you're transmitting your signal from the transmitter, you are using this frequency FC. So let's say I would transmit at 1 gigahertz. So I will use this frequency 1 gigahertz. Now, at the receiver, I would say, okay, I'm going to receive my signal at 1 gigahertz. But at the receiver, you have your crystal oscillator here. You have the oscillator which is going to generate this 1 gigahertz. And this you are going to multiply with your received signal. Now, whatever you do, you're not going to generate exactly 1 gigahertz at the receiver. Neither you're going to generate exactly 1 gigahertz at the transmitter. There is always going to be 1 gigahertz plus minus some frequencies. Why this is so? Because of the crystal that is being designed. So when you design a crystal or you design an oscillator, they are not exactly accurate. To get very accurate crystals or very accurate oscillators, you need very high engineering, very precise engineering, and very costly materials. So that increases the cost a lot. So what happens is at the receiver, when you're multiplying with this signal, it is never FC, it is FC plus some offset, delta F. This is the main problem here. So at the receiver, when you're receiving your signal, you're multiplying with the local oscillator. The local oscillator's frequency is never exactly same. It is slightly different. So therefore, what do you do? We'll see later how do we compensate for this change. So what happens is once you have this frequency offset, so when you multiply this particular signal, this carrier here, with your incoming signal, what you get is a e power j 2 pi fct multiplied by e power j 2 pi fc plus delta f t. And of course, then you pass it through the low pass filter, and the output you get is e power j 2 pi delta f t. So rather than getting a, or let me say AC, you are getting this component also, e power j 2 pi delta f t. And this we call it as a carrier frequency offset. Now, another thing also that adds up is the phase also. So here, what I assumed is that the phase is same, but you would not get the same phase. There will be also a phase shift in your signal. So there will be a delta phi also, and this delta phi is going to come here as well. So you will, so when you are multiplying your signal with the local oscillator, it will not generate, it will not have exactly the same carrier signal with the same frequency and the same phase. There will be a phase and the frequency offset. So these two are needed to be compensated in your receiver design. So all these compensations are never done in the analog part. It is all done in your digital part. Now what do you do is, you take your analog signal, which is now this, which is AC e power j 2 pi delta ft plus phi, and you take the symbol clock. Now again, the same thing happens with the symbol clock also. The symbol clock, so suppose you had this clock at the transmitter. At the receiver, the clock might have shifted a little bit here and there. This could happen. So let's say the clock had shifted. So if the clock shifts, then what happens is whatever signals that you are going to get are also shifted. So what happens is you are here placing the analog to digital converter, and you would like to sample your signal in middle of your bit periods. So when your signal, when your clock is skewed, when your clock is, there is a delay in your symbol clock, you're not going to sample your signal at exactly the same time as you would want to. And therefore, it leads to something called as a symbol timing offsets. So this also impacts the performance of our system. And once you have compensated for all these things, then what you do is you go for a signal demodulation. You take this A complex envelope and convert it into digital bits. And then the further processing happens, which is the channel decoding and the source decoding part. So what we are going to do in majority of the cases, we do not bother ourselves with the high frequency part. This is called as the pass band, or when you have your signal in the high frequency regime, we call it as a pass band. We never deal with signals in the pass band because it is impossible to do signal processing in the pass band. Rather than what we do is that we do all the processing in the baseband. So this side is your baseband. Here I have shown this is the analog baseband signal. So you down convert your signal. There is of course the frequency and the phase offset. And then you want to compensate for this frequency and phase offsets in your digital part of it. So you sample your signal and then you make all these corrections in your digital baseband. And therefore, this digital signal processing is very much important in communication systems for receiving the signal properly. So this is what I've explained. All the processing is done digitally at the baseband, and the carrier component is removed by multiplying the received signal with locally generated carrier. The receiver local oscillator has frequency and phase offsets, which you need to handle it at the baseband site. So therefore, digital signal processing is used to compensate for these offsets. Now, I am going to discuss some of these frequency offsets, though I have given you some idea of it, how these frequency offsets look like. But I'm going to discuss this in a little more detail. And I'll show you how we can compensate for these frequency and phase offsets. So first is your coarse frequency synchronization. What is the coarse frequency synchronization? Is that when you have your frequency offset, as I told you, in your local oscillator. So what happens is that, so suppose your spectrum was something like this. So here, this blue one is your spectrum that you transmitted. Okay. So this blue one, if you see here, this is your original spectrum. But because of this frequency offset, what you did is you multiplied your signal, your A. What you get is A e power j 2 pi f offset t. So what you're doing is you are shifting your signal by an amount f offset. So therefore you get a yellow curve here. So what you need to do is you need to take your signal, this signal, and you need to again multiply it with e power minus j 2 pi f naught t. Okay, so if you do that, then these two parts will cancel and you will again get back your original signal that you transmitted. Now, to do that, you need to first find out what is your f offset. What is your frequency offset in your signal? Now, the other diagram that I've shown you here, very important diagram. So when you're working on practical systems, you're going to see these things quite a lot. You will see, so when you plot the constellation diagram, you will see that the constellation that you're getting is not proper. So because of this frequency offset, what is happening? So suppose, I'll give you more intuition to it. So suppose you are transmitting a rectangular pulse. So this was your AC that you wanted to, you transmitted. Now, what instead you are receiving is AC e power j 2 pi f of t. This is what you are receiving. So what is this? Basically, it is AC cos 2 pi f of t plus AC sine 2 pi f of t. Let me plot the one part only. So if I plot this AC cos 2 pi f of t, it will be what? It will be a sinusoid here. So rather than getting a rectangular pulse, you get a sinusoid. And now what you do is, what is this constellation diagram? You now take this analog baseband signal and sample it to convert it into digital constellations. How do you do that? You sample the signal. At what times you will sample? Let's say at the middle of this bit period. At the middle of this bit period, you will sample your signal. So every time you're going to sample, because of this variation, you're going to see a different amplitude. Rather than seeing this amplitude, you're going to see amplitude changing in each of these bits that you are receiving. And therefore, you see how the constellation looks like is it keeps on revolving. And this is an indication that there is a frequency mismatch or there is a frequency offset in your received signal. This is a clear-cut indication. Okay. Now, how do you compensate for it? Very easy, very simple. I'll tell you how do we do that. So this is how we do that. I have written the formula here. So delta F is the maximum value of F for which this particular equation is satisfied. Now, what is Rm of n? It is your received signal raised to the power n. So I'll give you an intuition of why we are using such kind of a thing. So let's see the intuition. Now, you see what you're transmitting is, let's say, I'm transmitting a QPSK modulated symbol. So you have 4 modulated symbols. So these are 4. So if mathematically, if I want to write, my ST is A cos 2 pi FC t. Now, because of this offset, what you're going to get, you pass it through your receiver filter. You multiply it with the local oscillator, pass it through the low pass filter. So what you're going to get is your received signal to be equal to A cos 2 pi f naught t. Or in other words, in the complex notation, I can write A e power j 2 pi f naught t. Now, what is this A in your QPSK? So A can take one of these 4 values. So A is what? 1 plus 1j, 1 minus 1j, minus 1 plus 1j, and minus 1 minus 1j. Now, what do we do is we raise this received signal to the power square. Now, if I do that, what will happen? So if I write, so let me write r square. So if I write r square here, r square t, it will become a square e power j 4 pi f naught t. Now, what is a square here? So you have a this. So what will become a square? So for the first case, a square will become what? 1 minus 1 plus 2j. So it will become 2j. The second one will become 2 plus 2j. The third one will become 1 minus 1 plus minus 2j. Right? And the fourth one will become, okay, sorry, this is not 2. So this is 2j only. And the fourth one will become 1 minus 1 minus plus 2j. Okay, here it is minus 2j. Okay. So what happened if I plot these? So when I square these constellation points, what I get is 2 constellation points. So what I did is that I took my received signal and squared it. When you squared it, what you get is this A changes to A square, and these 4 modulation points now become 2. And you again square it. So let me write here R power 4 T is equal to A power 4 E power J 8 pi F naught T. So now what will happen? This will again square up, and what you're going to get is all minus 1s. Or rather minus 4, right? So essentially what you get is that this becomes minus 4 e power j 8 pi f naught t. This is what you get as r power 4. Okay, I have written a little slant. Let me write it again here. So r power 4t is minus 4 e power j 8 pi f naught t. And now if you take the Fourier transform of this, what you're going to get? You get a single peak at what point? 8 f naught. And this is what you detected. You detect this, this peak when you take the higher powers of this received signal. And from there, you can figure out what is your FF. So this is a very simple case of determining the frequency offset in your signal. and then compensating for it. Now comes the second part of it, which is the carrier frequency offset. Now in the carrier phase offset. So as I told you, there is a phase offset in your signal. So how your signal is going to look like now, RT is going to look like e power j phi. So this phi is your phase, that is the offset. Now when there is a phase offset, how your constellation is look like. So for BPSK, you had these 2 points. This constellation will rotate. So now you will get these 2 points. Rather than getting this point, you are going to get these 2 points because your constellation has rotated. Now to compensate for the phase offset, what you use is, you use closed loop compensator, which uses a PLL based algorithm. So what we do is, based on the different modulation schemes, what we do is we actually multiply these two symbols that you're getting. We multiply these two together, and from there we try to figure out what is this phase error. Right. So you can take the in phase, you can take the quadrature. That means you take the I and Q, both the axes, and then figure out what is the error, the phase error that is coming, and then you try to estimate that error and then compensate it. So this is the lambda n, that is your phase, and then what you do is, whatever signal you are getting, you just multiply it with this e power j lambda n to compensate for the phase. So this is how you do the phase offset. And the other very important part is the symbol synchronization. Now, as I told you that you need to sample your signal at exactly the required times. If you sample here and there, the thing will not make sense. I'll go back to the match filter part and show you why it will not make sense. So here, I showed you that this was my rectangular pulse, and you need to sample in between. So for a rectangular pulse, even if you have some errors in the sampling times, it doesn't make much problem. But of course, in reality, you do not transmit rectangular pulses. Rather, you transmit such kind of pulses like raised cosine pulses, Gaussian pulses, sync pulses, and so on, which is going to look something like this red curve here. So now if for the red curve, if suppose rather than sampling here at this point, if I sample a little bit earlier or a little bit later, you can see the very drastic change in the amplitudes. And this is the prime problem when you are dealing with symbol synchronization. You need to sample your signal at exactly the same times. So what is the solution to it? The solution to it is, what do you do is, over a bit period, so I'm going to show you with this example here. So this is your bit period here, or a symbol period. You sample it for 2 times. Rather than sampling it once, you sample it twice. So let's say you got these 2 samples. Or rather, let me take like this. Let's say this sample and then this sample. Or let me draw it even more better way. So this is my rectangular pulse. And this is my sync pulse that you formed. Now, you could sample it twice. So one time you sample it here, the other time you sample it here. Now, based on these different values here and here, you need to figure out how much adjustment I should make. So I should actually shift my sampling period to this side or this time to this side so that these values become equal. So what I will do is I will shift my sampling times to slightly towards left. So let's say I take this another one, so which is this one, and then this will go here. And then again compare these two. And once they come to the same level, then I can say, okay, the middle one now is giving me my proper sampling time. So this is what we do. We use, so there are different types of schemes here also. What we do is we try to take these samples, understand it, and write a algorithm which could tell me which side I have to do the sampling, how should I change my sampling duration, and then get the desired sampling intervals. Now, one major problem here is that now these signals that you are getting, you're processing is in the digital baseband. What is digital baseband? You have, so coming back again to my receiver part. So you're doing all this processing after this. So you're doing at B bar. Now, what happens? Once you have your continuous domain signal here, this is continuous analog signal, which is of course in the baseband. You have already done the sampling. You do not go back and do resampling of your signal. You cannot do it. If you do that, then you have to store that signal, that analog signal, and redo the sampling, which is not possible. Then what you do is when you are doing you are adjusting the sampling durations in your digital domain, what you do is you use something called as interpolation theory. So suppose if I have these two samples here and I want to sample at slightly different times. So what I will do is I will interpolate the signal in the digital domain and resample it in the digital domain itself. Okay, so this is what is done. Rather than doing everything in the analog domain, we do everything in the digital domain. So this is what I showed you. Because of the symbol synchronization, rather than seeing 4 constellations here, you're going to see such kind of a scattered plot. Because you're not sampling your signal at proper times, therefore you get noise. And to compensate that, we have a symbol timing PLL, again a phase lock loop. What it does is it first detects the timing error, which I explained to you the process, how it is done, and then determine, okay, how should I adjust the sampling times? And then there is an interpolator, which kind of gives you again a new samples based on the timing errors that you have detected. And once you have done all these things, then you go to the demodulation. So it's not directly that you jump to the demodulation and you're done. No, in practical systems, you have to do all these things before you jump onto the demodulation. And to demodulate your signal, what you get is you get a complex envelope AC plus some noise in your received demodulation received symbol, modulated symbol. Okay, and because of this noise, you transmitted this point, but you got these points. So you need to figure out whether this belongs to this or this belongs to this. And then there is a huge theory which revolves around maximum likelihood estimates or likelihood ratio tests and so on, which basically allows you to decide on to which modulation symbol that received symbol belonged to. And once you have detected that, then you can of course detect the bits. So then you are done. Okay. Now there is one more thing that is used in the communication system, and that is preamble. Now, what is a preamble? Basically, so take this as an example. Now you are getting signals when you are putting up your receiver. Your antenna is capturing your signals. It is sending it to your computer, to your digital signal processor for processing. Now you do not know when the received signal is going to come. The receiver may transmit now, or it may transmit at some other point. Now to detect that arrival packet, you use something called as a preamble. Now what is a preamble? Preamble is a set of known bits that you transmit, or known signal pattern that you transmit. So once you detect that known set of pattern, you can say, okay, now my packet reception has started. There are commonly known sequences that are used, such as Barker codes, Z of Chu sequences, and so on. Golden sequences, there are a lot of sequences. There you require certain properties of those sequences. One of the properties is that they should have a very high correlation. Cross correlation should be 0 only at exactly 1 point, so that when you're cross correlating, you should get a peak. Okay, when you're receiving a known set of bits, how do you know that you have received that known set of signal? You use the same signal in your receiver and correlate it. And when there is a peak in your correlation, you can understand that there is a preamble that is detected. There is one more usefulness of the preamble, and that is to also detect the phase shifts. I'll come to that phase shift part later, a little later. Or rather, I can explain it now itself. Okay. So let me explain to you now. So I'll go back to the phase offset part. Now here you got this phase offset. You could detect the theta here, and you were happy about it. Now the problem is that, so here you were having bit 0, this is bit 1. Now what could happen? The bit 0, rather than having shifted by theta units, it would have shifted to 180 minus theta units. So this could have been a 0, this could have been a 1. You never knew. So what you did is, when you rotated your symbols, so you made this as 0, this as 1. So what now? However, originally it was 0 here, 1 here, but because of rotations greater than 90 degree, you messed it up. You basically flipped the bits. So this is what generally happens in your communication systems. You never know what the phase offset is going to be. And so this preamble, which is a set of known bits, is used to correct that shift also. When you receive the preamble, you can also understand by what phase your signal has changed in the multiples of 180 or 90 or so on. And that could be corrected using preambles. So this is another part of another use of the preamble. Now, so with this part, I'm almost done with the theory part of the communication receiver part. And let us also understand what kind of channels we are looking at. So the first channel I'm going to look at is the additive white Gaussian noise channel. So this is a very basic channel that is used in the communication systems. And it is good for satellite and deep space communication links where there is no path loss, where there is no multipath, no signal dispersion, no non-linearities, and so on. Now this has 4 parts to it. AWGN has 4 parts to it. One is the additive. It means that the noise is additive. So with the signal, the noise adds up. Then we say it is white. White means that the noise is uncorrelated. White means the power spectral density is flat. So if you draw the power spectral density Sn of f versus f, so it will show you a flat power spectral density. So if you take the autocorrelation, you take the inverse Fourier transform of this, you get the autocorrelation, and that will be a delta function. So this is the autocorrelation. So what it tells you is that, suppose if I measure the noise now, and I measure the noise exactly just after this. So what happens? This noise remains uncorrelated. Okay. So, so this is about the white. And what is Gaussian? Gaussian means the PDF of the noise that you're going to get will be of the Gaussian nature with mean 0. So this is a PDF of the noise. So let me write Pn of t, Pn, and this is n. So the noise amplitude will be distributed in a Gaussian fashion. And of course, it is a noise. So this is about the AWGN channel. The wireless channel we are going to discuss in the next session. And mathematically, we model the AWGN channel using this command RT, which is the received signal, is equal to xt times xt plus nt. So xt is your transmitted signal, and nt is your noise that you added. And in MATLAB, it is very easy to generate this noise using the rand command. And the one last part that we talk about in a communication system, how do we analyze the performance of different modulation schemes, is using some parameter called as the bit error rate. Now, what is the bit error rate? So I'm taking this example of a BPSK signal. Now for BPSK, you transmit two symbols. So one at plus something, the other one at minus something. So let's say this is bit 1, this is bit 0. Now when you transmitted the signal, and you receive the signal, the noise gets added up. And what happens is that this amplitude of the signal changes when the signal is received over the channel. Now, because I'm taking the AWGN noise, additive white Gaussian noise, how the amplitude is going to change? So amplitude will be this particular one, plus it will add the Gaussian distribution, okay, here. So therefore, you see the amplitude that you are going to get will follow a Gaussian distribution with mean S1 hat. And similarly for bit 0, again the noise will be added up, and the PDF of the amplitude that you get for bit 0 is again this curve here. And now you can see if the noise is pretty more, then suppose you transmitted bit 1, you could receive an amplitude which is less than 0, and vice versa. So these are the points where you are going to incur errors. What is your decision boundary? Decision boundary is the point in between the two symbols. So this of course for BPSK turns out to be 0. For the other cases, you can have different boundaries. So based on this decision boundary threshold, you can have this Gaussian curve, and you can figure out what is the error incurred when you have these Gaussian curves. When you have the signal corrupted by noise, then you can quantify the error. And what is the error? Error is this area under this curve. So this is the probability with which you are going to make an error. And when you add these two errors together, so this error, because this is the Gaussian distribution, so the error will be integral of this Gaussian from this point up to the plus infinity point, which comes out to be the Q function. So you can write it in terms of Q function, and then you add the errors from both the bits together. And you also multiply the probability of these bits being transmitted, and finally you get the bit error rate. So this is how we basically obtain the bit error rate for any modulation scheme. And this I showed you for a simple BPSK in AWGN channel. And for the different modulation schemes, I have summarized the bit error rates here. Here we have the graphs also I'm showing. And important point to note here is, so one thing is your SNR is in dB. So as you keep on increasing the SNR, your bit error rate keeps on decreasing. So you can see the bit error rate is decreasing as we are increasing the SNR. That is the first point. The second point is that here, that as you go to higher modulation schemes, your bit error rate increases. So for a given SNR, as you keep on increasing the modulation order, your bit error rate keeps on increasing. So these are the two things. And in 5G systems, we use adaptive modulation and coding schemes. In that, based on the SNR that you are experiencing, you change your modulation scheme. Okay, so this is one of the application areas. So these are the references that I've used. Let me go to the MATLAB now and show you some of the codes for our communication system. Okay, before that, if anyone has any doubt, I would be happy to take it up. Yes, Vishnu.
Sir, good afternoon, sir.
Good afternoon.
Sir, can you please elaborate that you said when we go for higher modulation rates, the bit error rate will be more.
Yes, okay.
But generally, we will move to, when we go to real communication, we prefer 8 PSK, 16 PSK.
Yes.
But when the bit error rate is increasing, how it is justifiable, sir?
Yeah, you can see this one. This I showed you for different modulation schemes. You have the constellation diagram.
Yes,
so let
sir.
me compare QPSK with 64 QAM. Let me show you this. Now in QPSK, suppose you have noise. So if you get this particular symbol, if it goes to here, your decision boundaries are these for QPSK.
Yes, sir.
So you can easily detect, okay, it was the symbol that you transmitted. Now, can you do that with the same accuracy for for 64 QAM? So suppose you have this symbol here and you got it here because of the noise.
Yes.
Can you still get this to here? No. You will probably detect this to be one of these four.
Yes.
Right. Now, this is the problem. As you keep on increasing the modulation schemes, you kind of congest your constellation diagram. That means these symbols, the complex symbols that you're transmitting very close by.
So what will be the remedy, sir, then? Because when we go for real modulation, real communication, we generally prefer higher modulation schemes only, right, sir?
Yes. So as I said, in practical systems, what you do is based on the SNR that you are experiencing, the signal to noise ratio, you change your modulation scheme. So if you are experiencing a low SNR, you go for a lower modulation scheme.
Okay.
So that you get less errors.
Okay,
If
sir. Thank
you have higher SNR, then you go for higher modulation schemes.
Sure, sir. Thank you, sir.
Yeah. Any other question anyone has? Otherwise, then we'll move to the MATLAB part. I hope my MATLAB is visible to everyone.
Yes, sir.
Okay. So I have pre-written some of the codes for you, but I will go through each of these together. We'll go through these together. Okay, so the first code I'm going to show you is for the AWGN noise, the additive wide Gaussian noise. Now, I use these 3 lines in each of my codes. Why do I use it? Because you see, this is my workspace. If you see here on the bottom left, if you see, there is a workspace. It has all the variables that I kind of generated in my past running the code. So I don't want these variables to interfere with my variables here that I'm using in the present code. So I use clear all. So what clear all does is that it removes all the variables that are there in my workspace. Then I use close all. Close all if some window is opened. For example, if some figure file is opened, then it closes all those things. And then I have a CLC. CLC means I clear my command window screen so that I start with a fresh slate. Okay, just like you go to the classroom and erase everything and then you have a fresh beginning. So that's our fresh beginning here. In MATLAB, it is very simple to generate the additive wide Gaussian noise. You just need to generate certain Gaussian random distributions. It could be easily done using the rand_n command. So here I'm generating the rand_n 5,000 numbers of these Gaussian distributed random numbers, which I term it as noise. And then I'm going to show you the plot of this these noise. So I'm showing you 4 plots here. One is the normal noise, and you can see it is really random. The other one I'm going to show you is the histogram. Now, in continuous domain, I talk about PDFs, the probability distribution functions. However, in these are digital systems, I cannot compute the PDF. So what I need to do is I plot something called as histogram. So the histogram gives me a fair idea about the distribution of my numbers that are there. And then I'm showing you the power spectral density. So as I told you, the power spectral density of an additive white Gaussian noise should be looking something like a flat, and the autocorrelation should look something like a delta function. So we are going to see that part. So let me run it. Okay, 1 second. Yeah, so here you get it. So the first graph on the left shows you the noise, which is truly random. The second shows you the histogram. You can see it follows a normal bell-shaped curve. The third plot is the power spectral density, and you can see it is almost flat. So it is around -5 dB. And if you plot the autocorrelation, there is a delta at 0, and then you have very small values for other times. Okay, so this is how you generate a noise, an additive white Gaussian noise in MATLAB. Now coming to the BPSK simulation. So this is a very basic simulation of BPSK that we are doing. So what we are going to do is we are going to generate a few bits. We're going to modulate it into a BPSK modulation. And then what we are going to do is that we are going to pass it through a matched filter, a pulse shaping filter, and then pass it through a channel, an additive white Gaussian noise channel, and then receive it after passing it through a received filter. And then we will try to demodulate our signal and get back the original signal. This is what we are going to do. Okay, so let's proceed. So this is the number of bits that I'm going to use, which is 10 to the power 6. See, in simulations, this is very important. The amount of message signals that you're transmitting is very important. See, this simulation, how it works on, basically there are certain rare events that you want to simulate, and you want to average all these results into one number. So what you need to do is you need to average it over all randomness of the signal that you can possibly generate. So the larger the number of bits you are going to take, the better is your accuracy, the better result you are going to get. I've seen a lot of people working with very small numbers. They will take 10 bits, 100 bits. It is not going to give you nice results. You must take large number of bits. Okay. Then what I need to do is I need to generate random bits. So this is the randi command that I've used. It takes bits 0, 1, 0, 1s, and then it plots, and it actually generates these random numbers. For how much times? For num of bits times. That means 10 to the power 6 times I generate these bits. Okay. Then what I need to do is I need to modulate this. I need to convert these bits to a complex symbol, complex modulated symbol. How do I do that? I'm using BPSK. So what I will do, I'll take one bit at a time, and I will see if the bit is 1, I give it 1 plus 0i. If the bit is 0, I give -1 -0. Don't worry about these lines here. I'm just commenting it here for the time being. I'll show you the applicability of this later. So this is how you get your signal, your modulated symbols, which is in the complex form. Now I showed you for a very basic case of BPSK, but you can you do it for QPSK, for QAM, and so many things by just changing these values here. So you could have different cases, and for each of these different cases, you will take the set of bits and you will convert it into a complex modulated symbol. Now what I should do is I should pass it through my filter, raised cosine filter. To convert it into a, rather than using a rectangular filter, rectangular pulse, I'm going to use a raised cosine pulse. So this is how I use it in MATLAB. I use this COM toolbox, which has this particular filter setting. So I make a filter out of it and pass my mod out signal. This is my mod out signal. I passed it through this transmit filter. And that one, then what I'm doing is that I want to analyze the spectrum of this signal. So let's do that. So let me show you how the spectrum looks like.
Hello, sir.
Yes.
This is Dr. Nokula Srinivasan.
Yes.
Oh, you are using raised cosine window.
Yes.
What is the advantage? Why not other windows, Bartlett and triangular?
Okay. See.
To get Gaussian and this eye diagram purpose.
See, again, coming back to the pulse shaping, if you use a triangle, what will be the Fourier transform of this?
Triangular.
It will be sinc square,
yes,
right?
Sinc pulse, yes.
Now it will be something like this.
Sin theta by theta form.
Yes. Now you know that's why we don't want to use sinc in the frequency domain, because sinc goes from -infinity to infinity.
Yes.
So it takes complete wide spectrum, something
Yes.
like this.
Okay.
And therefore your signal will not be band limited.
You want finite impulse response windowing technique.
I want, yes, finite impulse response of course is there. And also I want my signal to be band limited in the frequency domain. Because suppose if you are transmitting two signals side by side,
Agreed.
they should not interfere.
Got it. Thank you.
Yeah. So I was actually showing you the, may I take the questions later if it is okay?
Yes, sir. Sorry.
Yeah. Okay, so I was showing you the spectrum plot of the BPSK modulated signal after passing through the raised cosine filter. So you can see the blue one is my bits that I transmitted. It took almost a lot of spectrum. And when I passed it through my raised cosine filter, you could see the spectrum shrink to this only portion. So this is the utility of the raised cosine filter. It basically limits your spectrum. But I also want to show you how my signal looks like when I pass it through a raised cosine filter. I want to show you that. So what I'm doing is, now one thing to note here is these are all digital signals. We are working on a digital system. So when we talk about rectangular pulses, or we talk about these digital modulation symbols, we say over a bit duration, this is the value that I want to transmit. Now, when you're using a rectangular pulse, you can just say over this particular period, let me show you, it will become even more clearer. So okay. So this is the pulse that I'm transmitting over a symbol duration. This is my T symbol, let me say. Now, this is one point that I get. From the set of bits, I made my complex modulation symbol, and that is one value that I get. Now, if you're using a rectangular pulse, I just require to specify only one bit, only one point here. But suppose if I'm using another pulse shape, say for example, a raised cosine, So it will look something like this. And to denote this, you need multiple samples, 1, 2, 3, 4, and so on. So, okay, so you got the idea. So if you were using a rectangular pulse, you just required one sample. But if you are using a complex pulse, you require multiple samples to show the shape of that pulse. So what here we do is, when your signal passes through the raised cosine filter, this transmit filter, what it does is, it upsamples or it increases your samples 8 times. 8 times, it increases the samples and then applies the raised cosine filter on top of it. So whatever number of samples now you are going to get is 8 times. Rather than getting one sample per symbol duration, you're going to get 8 samples per symbol duration. So this is an important point. So I'm going to show you both the signals side by side. So one is the rectangular pulse and other one is the signal that you got after passing through the raised cosine filter. So let me plot it. So it is running, just wait for a minute. Yeah, here we get. So here you can see the blue one are the rectangular pulses. So 1, 0, 1, -1, 1, -1, and so on. And the black one shows you the raised cosine pulses that we used. And you can see that it's not flat, it's not very simple to see. It's really tough to understand these signals. And therefore, the whole idea of sampling at the right times is very important, very critical in such kind of setting. All right, now let's move forward. So after this, what we do is we form a receive filter and then we define an SNR, okay? So let's say we take SNR from -20 to 10 dB. Then we take our transmitted signal, pass it through the AWGN channel. So this is the command that we use in MATLAB to pass our signal through the AWGN channel. And then we take the output. So once the signal is received, we pass it through the receiver filter to get the output signal, of the receiver filter. So that means, what is a receiver filter? When you transmit these cosine pulses, what happens is that you need to reverse it at the receiver side. You need to again apply this filter, or we call it as a matched filter, so that you get your signal again. Just a second. Yeah, hello.
Sushant sir?
We will then break for lunch at this point.
Yes.